Assalamu alaikum. Welcome to this class. In this class, we'll be discussing about the different methods that are used to control the voltage. As we know, as the load changes, voltage also changes. So, to have a specific, or we can say, to control the voltage over a specific limit, we need two different type of methods to control the voltage. So, the first method is we control the voltage by reactive power injection. At the receiving end, we know that as the reactive power demand increases, the receiving end voltage will decrease. So to increase that voltage, we'll actually supply that reactive power locally so that the demand for reactive power is not from the source, it is supplied or it is met locally to the load. And in that case, this receiving end voltage will not drop significantly. As we know, QR is equal to Vs minus VR into VR by X, or we can say this difference of the voltage from source end to receiving end is proportional to the QR, that is receiving end demand, load, reactive power demand in the load side. Lower the value of the QR, that is the reactive power demand, lower will be the value of this difference, Vs minus VR. Or if this is higher, we can still make this lower by injecting some capacitive reactive power at the load end at full load if we have a higher value of this difference, positive higher value of the difference. In that case, we need a capacitive reactive power at full load, and we need an inductive reactive power at no load, because at no load you will see this will be negative and this will also be negative. Just to consume that reactive power, we need to supply the inductive reactive power, or we need to use this inductor at the source end to consume this much of the reactive power if it is supplying to the source. So in that case, we might make this Vs minus Vr equal to closely equal to 0. So usually without compensation, this QR is equal to QD. Receiving and reactive power will be same as the total demand. So with capacitive compensation, this QR is equal to QD minus this QC. In that case, this QD will be positive. This QC has to be negative just to cancel out this or make this very small, and in that case delta V will be positive before using this QC. When this QC is used, we can make this delta V equal to be 0 as well. So with inductive compensation, this QR is equal to QD plus QL. Delta will be negative. In this case, this QD will be actually negative, and we add this QL, you will see this can also be made to be equal to 0. In that case, we'll also make Vs is equal to VR. So this is how this reactive power injection can be used. This is actually used. This is used by two types of reactive power injection. One is static var generator, that is capacitor, or we can use inductor as well, because for Ferranti effect, we can use the inductor to consume the supplied reactive power by the shunt capacitors of the transmission line. Static var generator in general, it can be capacitor or an inductor, or rotating var generator. It is a synchronous condenser. It's actually a synchronous motor which is connected to the system at no load. That is known as synchronous condenser. Actually, it acts exactly in the same manner as that of the capacitor. It has slightly more advantages as compared to capacitor, because whenever the voltage is high, this capacitor provides more reactive power, which is at that time it is not needed. When voltage is low, when this is very required at that time, it provides less reactive power. That is why we can say this is not a reliable friend. This is the reliable friend. It provides the reactive power independent of the terminal voltage. We have some other FACT devices, flexible AC transmission system devices. In that case, we use the voltage control device as static var compensator. It is also known as SVC. These are actually, please try to remember that these are actually thyristor controlled inductors and capacitors, static var compensator. So another is STATCOM. STATCOM is static synchronous compensator. They are actually not thyristor controlled. They are actually used by the IGBTs, or we can say MOSFETs, or other switches which are bidirectional, since we know that, or which are fully controlled. This thyristor is not fully controlled, it is half controlled. We can switch it on, but we cannot switch it off. But here we have IGBT, STATCOM, we have BJT. They are fully controlled. We can switch them off or on as per the convenience. So in case of STATCOM, it is the fully controlled switch that is used. So these two are used for the, and in this case, uh, this is similar to that of the synchronous condenser, and this is similar to that of the capacitor, because uh, it also has a problem of providing less voltage when the voltage is providing less reactive power when the voltage is less. But this has not such kind of a problem. Now we can use another method, that is by the control of the transformers. We know that the transformer directly changes the voltage by changing their turn ratio. Such type of transformer is known as the tap changing transformer, or sometimes OLTC, that is on load tap changing transformers. You might have seen them in most of the grids. It is this OLTC, that is on load tap changing transformer, which is installed. So we can use them directly to control the voltage as per our need, but they itself does not provide the reactive power. They put that burden, that is the providing the reactive power, to the source. So that reactive power has to be then supplied by the source. This is a type of a tap changing transformer which is connected at both the ends for the transmission line. This is how it is connected. So we can change this over here, voltage will be reduced. We can change to this, again reduce. If we decrease it, voltage will be increased over here. Similar is the case for this. If we reduce over here, the number of turns will be reduced and voltage will be reduced. If we increase from this to this, voltage will be increased. This is 1:TSN1 is the turn ratio of the source and transformer. This is TRN2:1 is the turn ratio of the load end of the transformer. And the third one is a control by the midline boosters. We are using a booster transformer connected in series at the middle of the or intermediate of the line. So what are these R1 and R2? These are actually, we can see, circuit breakers. If we have to use this with the line, we can put this, we can switch on to this, switch on this R2 and switch off this R1. In that case, this will come in the circuit. And if we have to put it off, we can switch off this R2 and switch on this R1, and in that case we will bypass this. So this is why R and R2 are there. So what booster transformer will be doing when a current passes through this, it increases the voltage of the line and it increases the voltage of the receiving end as well. The voltage drop will be reduced. When the current reduces, their voltage drop will also be reduces. This booster transformer is a type of a regulator. It increases the voltage when load increases. It decreases the voltage when load decreases. That's why it has that type of an advantage. These are used to increase the voltage of the line at the intermediate points rather than at the ends, as we have seen for the OLTC transformers. And boosters are generally used in distribution feeders. They are usually used in distribution feeders because in case of distribution feeders, the voltage drop is predominant, as in the case of as compared to the transmission line. So this was all about the performance of transmission line. So let us try to do some more numericals on transmission line, and then we will finish it. Find the parameter C if A and B respectively are given as A is equal to 1.5, B is equal to 50, that is A is equal to 1.5, B is equal to 50. And since we know that for transmission line it is symmetric, A will be equal to D, that is equal to D will also be equal to 1.5. And by using the reciprocity property of the transmission line, we can calculate over C. So AD minus BC is equal to 1. That means C is equal to 1 minus AD divided by B. Now, no, it will be AD minus B, AD minus 1 divided by B. AD is equal to AD, A and D are same, that is 1.5 square minus 1 divided by 50. It is equal to 0.025 ohm inverse. The next one, the constant A of a 220 kV transmission line is 0.94 at an angle of 10 degrees. When the transmission line is system voltage is given, it means this system voltage is usually taken to be the receiving end voltage. If the sending end voltage of the line is given at a load delivered, for a given load delivered at the nominal voltage is 240 kV. This is the sending end voltage. when the nominal voltage is given at the receiving end and it it is delivering the full load at that time. Vs is equal to 240 kV. Find the voltage regulation of the line. So for calculating the voltage regulation, we know that voltage regulation is equal to magnitude of Vs divided by A minus Vr divided by Vr, where Vr is equal to 20 kV, Vs is equal to 40 kV, and A is equal to 0.9594 at an angle of 10. Since we are only interested with the magnitude of the A, that means this will be equal to 40 divided by 0.94 minus 220 whole divided by 220 into 100. It comes out to be 16.05%. Next one, a transmission line has a source voltage as 220 kV and it is delivering a power of 60 MVA at 0.8 power factor lagging. Given that A is equal to 0.93 plus J 0.016 and B is equal to 20 plus J 140, find a receiving voltage. Usually in questions it is given that receiving end voltage and we are usually asked to find out the sending end voltage, but here it is other way around. You are given the sending end voltage, we need to find out the receiving end voltage. It is simple, but it requires solving the nonlinear equation. So A is this, B is this, and Vs is this. So this is the magnitude of the, or we can say apparent power, that is 60 MVA. It is 60 MVA, and the load power factor is 0.8 power factor lagging. So IR will be equal to SR divided by VR. It will be equal to 60 into 10 raised power 3 divided by VR amperes. If I take it into kiloampere, it will be equal to 60 divided by VR kiloamperes. So I have to use it in kiloamperes, and I will tell you why. Now, using this formula, I can calculate simply this VR by using this formula. So Vs is equal to AVR plus BIR. Now, as usual, we're taking VR as a reference, and when VR is as a reference, and Vs will be definitely at some angle delta with respect to VR and a positive delta, because power will be supplied, real power will be supplied from Vs to VR. Now, giving the value to this Vs will be equal to 220 at an angle of delta is equal to AVR. A is 0.93 plus J is 0.016. VR at an angle of 0 plus 20 plus J 140. This is B into IR. IR will be this. Since this VR is in kilovolt, it will be its unit will be kilovolt. This is also in kilovolt. Its unit is kilovolt. I have not used 10 raised power 3. I have dropped that 10 raised power 3. Since this is in ohms and this has to be in kiloampere, so that this term will be in kilovolt. That's why I have used this IR in kiloamperes to get, when I multiply the ohms to this, I will get kilovolt. So I hope you understand this point. So writing them in rectangular form, this will be equal to 20 cos of delta plus J 220 sine of delta, and this is as it is. So this is, I have taken this VR to this side, and when I write this in terms of rectangular form, it is 48 minus J36. Now writing again, actually I have to solve this. So when I solve this, I get 6000 plus 6000 J divided by VR. When you multiply this this term to this term, you will get this term. So now separating the real and imaginary parts, we get that means 220 cos of delta will be equal to 0.93 VR plus 6000 divided by VR, that is this. Similarly, 220 sine of delta is equal to 0.016, that is this, and 6000 divided by VR. These are these two equations. Now these are two equations with two variables. One is this, another is this. Sorry, this is one variable and this is another variable, VR. So I can omit this by squaring and adding these two equations, and I do that. So it comes up 220 square is equal to 0.93 plus 6000 divided by VR square plus 0.016 VR plus 6000 divided by VR the whole square. In this case, you can see that this delta has been eliminated. Now this is the equation, only one equation in VR, only one variable, but it is a non-linear equation. So you can use this equation, or you can write this equation directly on the calculator and solve for any value, for any initial value, because usually nonlinear equations are calculated or solved by using the iterative method, and iteration in the calculator that we are usually using, that is FX991ES plus. In that case, it is very easy. In that calculator, you can use this equation, put the equation as it is, and solve it. You will get the answer. This is 201.94, which is approximately equal to 202 kV. I have actually made a video for this, how to calculate, how to solve this equation. I will share that link also in the description of this video. You will use that and try to try at your own at your own how to calculate such nonlinear equations. Now moving to next problem. This is related to power flow problem. A 275 kV transmission line has the following line constants: A is equal to this and B is equal to this. Determine the power at unity power factor that can be received if the voltage profile at each end is to be maintained at 275 kV. This is part A. So part B is what type of the rating of compensating equipment would be required if the load is 150 megawatt at unity power factor with the same voltage profile. So we have to use the same thing, but we have to increase the power from, we have to use this much of the power, and we have to find out the compensating equipment, that is reactive power injection equipment. With the load in part B, what should be the receiving end voltage if compensating equipment is not installed but unity power factor is maintained? Let us try to find out the first one, that is power. We need to calculate the power at unity power factor. Receiving end voltage and sending end voltage are same. That is what this point means. From this to this, that is at 275. So Vs is equal to 275, A is equal to this. That means alpha is equal to 5 degrees, beta is equal to 75 degrees from here. So Vr is equal to also 275 degrees because both are maintained at the same voltage. So PR is equal to Vs Vr by beta cos of beta minus delta. That is a relation of PR minus A by B Vr square cos of beta minus alpha. It is to be calculated. And QR is equal to same thing, only in place of cos we have sine. Since power factor is unity, QR has to be equal to 0. So when QR is equal to 0, that means this term should be equal to this term. So that means Vs Vr, which are both equal to 275, that means 275 square divided by B is equal to 200. Sine 75 minus delta, 75 is beta, that's beta minus delta, is equal to A is 0.85 divided by 200 into 275 square into sine of 75 minus 5, beta minus alpha, alpha is equal to 5 degree. By solving this equation, delta can be calculated as 22 degrees. When delta is calculated as 22 degrees, I can put delta over here. At this point, I can get the value of PR. So PR is equal to 275 square divided by 200 into cos of 75 minus 22 minus 0.85 into 275 square divided by 200 into cos of 75 minus 70. That comes out to be 117.63 megawatts. This is the this receiving end power. Similarly, now the second question is, we need to find out the compensating equipment rating if the voltage profile is same as that of this and load is 150 megawatt. So here it is given that load is 150 megawatt. That means we have to use the same formula. The only variable here is delta. So you can simply calculate this delta by solving this equation, and this delta comes out to be 28.48 degrees. So from here I get the delta. Now I have to calculate the rating of the compensation equipment. So when I do that, I need to calculate QR, which is equal to QD. That is equal to 75 square divided by 200 into sine of 75 minus 28.46. That is this delta minus, this is the constant term independent of delta. It comes out to be minus 27.56. That means without a compensating network or compensating equipment, the reactive power is negative. That means the load is supplying reactive power back to the source. So this much of reactive power has to be consumed. I have told you in the beginning that when the reactive power is negative, it has to be consumed by the inductive reactive power or inductance by placing the inductance at the receiving end. So since power factor has to be unity, that means all this reactive power has to be consumed by the inductive reactive power. Again, that means QR has to be equal to 0. That means QD plus QL should be equal to 0. Since QL is the inductive power. Since QD is negative, that means QL is equal to 27.56 MVR. We have to design a QL, that is an inductance whose reactive power consumption capacity is 27.57 MVAR. In that case, this reactive power, power factor will be unity. Now, the last part of this question is, with the load in part B and unity power factor maintained, find the receiving end voltage if the compensating equipment is not installed. Otherwise, when the compensation equipment is installed, it again makes the receiving end voltage equal to the sending end voltage. So in this case, PD is equal to PR is equal to 50 megawatt. Again, QR is equal to 0. We need to find out VR. So using the equation of the QR, that is 0 is equal to QR. This is VS VR divided by 200 sine of this beta minus delta minus 0.8, that's A by B, sine of 70, that is 75 minus 5 into VR square. So it means sine of 75 minus delta is equal to 3.091 into 10 to the power minus 3 VR. After calculating these two terms, VR here 1 and VR here will cancel out, 200 will cancel out. This 3.091 is 0.85 divided by 275. So using for the real power, it will be equal to 150 into 275 into VR divided by 200, cos of 75 minus delta minus 0.85 divided by 200 into cos of 70 into VR square. So by simplifying certain values, it comes out to be this value, and then cos of 75 minus delta is equal to 1 minus sine square theta, that is 1 minus sine square 75 minus delta, that can be taken from here, that is this 3.091 into 10 to the power minus 3 VR. So putting this value over here, I get 150 is equal to 1.375 VR into 1 minus 3.091 into 10 to the power minus 3 into VR whole square minus this term. So after solving the above equation, this is again a non-linear equation. I have to solve it as I have solved the earlier equation. I get this VR is equal to 244.9 kV. These non-linear equations are very simple. When we solve them on the calculator, you just have directly put the equation as it is on the calculator and give some initial value close to the Vs, which is already given. So you will get this value. Now, one more problem. This is related to the modification of the ABCD parameters. In this case, the ABCD parameters of a three-phase overhead transmission line are given as A is equal to D is equal to 0.9 at an angle of 0, B is equal to 200 at an angle of 90 degrees, that means 200J, it can be taken as 200J. C is equal to 0.95 into 10 to the power minus 3 at an angle of 90, it can be also taken as J. At no load condition, a shunt inductive reactance is connected at the receiving end of the line to limit the receiving end voltage to be equal to the sending end voltage. Usually, we know that for a transmission line, especially for a long transmission line, at no load, receiving end voltage is more than the sending end voltage because of the Ferranti effect. So here, to compensate for that, we use an inductor at the receiving end at no load, so that receiving end voltage is equal to sending end voltage. So we need to find out the ohmic value of the reactor. So given A is equal to D is equal to 0.9, it's a real value, I can drop this, and C is equal to 0.95 into 10 to the power minus 3J, and B is equal to 200J. So this is the uncompensated network. In this case, VR will definitely be greater than VS. So we need to find out the actual value of this, so that is VR will be equal to VS. So here, let us say this is IR dash, and from here, this IR will be equal to current flowing through this plus this IR dash. That means this IR will be equal to IR dash plus VR divided by Z. This VR will remain as it is because this will be common to this or parallel. Now writing the ABCD parameters without the compensator, it will be VS is equal to AVR plus BIR and IS is equal to CVR plus DIR. So we need to find out the ABCD parameters in terms of VR and IR dash, because now the system is like this and output is this, not from this. So our ABCD parameters should be in terms of VR, because VR will not change, it will be directly connected over here. What will be the voltage over here, same as the voltage over here, but the output current will change. Earlier it was IR, now it is IR dash, output current. So we need to represent ABCD parameters in terms of VR and IR dash. So IR will be equal to IR dash plus VR by Z. Here it is not IR dash, it is only IR. IR will be equal to IR dash plus VR by Z. Put this IR in this, and in this I will get the modified ABCD parameters in terms of VR and IR dash. So VS is equal to AVR as it is, because VR not change, this IR will change. B into IR dash plus VR by Z. This VR by Z. So separating the terms VR and IR dash. So VR has two terms, that is, one is A into VR and second term is B by Z into VR. So taking VR common, VR will be, this will be equal to VS is equal to VR into A plus B by Z plus B into IR dash. IR dash is only one term, that is B into IR dash. So this Vs will be equal to A plus B by Z into VR plus B into IR dash. Similarly, when I put this IR, which is equal to IR dash plus VR by Z at this point, I will get IS is equal to C plus D by Z into VR plus D into IR. So these are the modified ABCD parameter equation. Now A will not be equal to simply A for this IR dash for new transmission system. A will be equal to A plus B by Z. Now the condition is we need to design it in such a way so that the receiving end voltage should be equal to the sending end voltage. And one more thing, you can see just the B is given as 200 angle of 90 degrees. B is given as 200 angle of 90 degree and Z is inductive. It means it will be having all, it will also have an angle of 90 degree. This is 200 J, this will be, let's say, ZJ. So what I mean to say is that this B by Z will be a real number. It will not be having any angle. A is already a real number because its angle is already given to be equal to 0. So we need not to do the complex calculations. We need to do the real calculations only. So at no load, it is given that Vs is equal to Vr. So using equation 4, we get when Vs is equal to Vr at no load, that means this has to be equal to 0. That means Vs is equal to A plus B by Z into Vr, because no load IR is equal to 0. That is what I have written over here. And for Vs is equal to Vr, this and this will cancel out. This will be 1 is equal to A plus B by Z. I repeat here its angle is 0. This is also a real part. I'll first mention this because it is given that magnitude of this and this will are equal, and since I have omitted the angle, their angle has to be same, then I can cancel them out. So from here you can see their angle will also be equal to 0. Usually, since we are taking this to be reference, its angle will be 0. Its angle B is 90, its angle is 90, they will cancel out. So it will be a real number. It is already given to be a real number. So total real number multiplied by real number, it will be a real number. Its angle will also be equal to 0. So in that case, I can cancel directly Vs and Vr. So it will be equal to 1 is equal to A plus B by Z. I have to calculate this Z. A is given, B is given. So 1 minus A is equal to B by Z. So Z is equal to B divided by 1 minus A. So this is 200. This is 1 minus 0 0.9. Is it 0 0.9? Yes, A is equal to 0 0.9. So finally, this is equal to 200 divided by 1 minus 0 0.9. It comes out with 2000 ohms. Okay, thank you.